Good afternoon. Today we are starting our presentation on the Space Habitat Challenge. Since time immemorial, humans always had the tendency to explore what's beyond their horizon. This propelled them to explore the land, the ocean, the sky, and now humankind is on a journey to explore other worlds that are beyond the Earth. Space exploration involves huge risks, but the advantages heavily outweighs the risk involved. With advancing science and technology, coupled with proper planning and execution, humans are close to becoming a multi-planetary species. This is our report contents that we are going to discuss today. There are several challenges ahead while choosing the new world. Some of them include amount of information available, topographical data, distance, nature to the celestial body, possibility to sustain life with the aid of technology, availability of local resources. Our proposed solution to all these challenges is Mars. Mars has been a long source of fascination and inspiration for humans. The establishment of colony of Mars has been the dream of humanity for decades. 99.1% of the Martian surface has already been mapped, which shows that Mars to be one of the most suitable extraterrestrial destinations for establishing a human habitat. The plants invite craters, deserts, valleys, polar ice caps, rotational speed, axial tilt are also very remnant of our planet. Life on Mars requires access to water. On the surface of Mars, water is predominantly present as glaciers. Launch window to Mars occurs every 26 months, and Mars is a wonderful first step for humanity. With the help of advanced technology, it is possible to live in these hostile environments. It is almost in the Goldilocks zone. It can also provide a lot of local resources. One of the challenges is to discover a location on the Mars that can provide enough in situ resources, habitat building ingredients, suitable landing sites, and site for power production. It also has suitable environment conditions for building a colony. The location of Erebus Mountains is the most viable location for this habitat. It is 811 kilometers across and is located in a group of mountains in the Dakarian quadrangle located at 35.66 degree north and 185.0 degree west. This location is not too far from the equator, thus experiencing a adequate amount of sunlight, and it is also closer to the polar ice cap, keeping the climate very steady. From the topographical map of the Erebus Mountains, it is clear that the land is relatively flat, thus providing suitable surface to build multiple habitats, landing sites, and easy transportation. With extensive study of flow patterns in this location show promising ice accumulations. This deeply covered glacial land systems can be utilized as a source of water and is easily accessible by the Martian crew. Topographical emission spectrometer mission of NASA has suggested large amount of basalt rocks. Our mission plan. On 15th of August 2069, Homo sapiens from the planet Earth will set foot on Mars, making a major milestone. The advance in technology has propelled us to put a life on the Mars. The establishment of the human habitat poses an entirely different set of challenges, yet we choose to defy the odds in the pursuit of being a space-faring species. The on-site planning of the Martian habitat will begin approximately 1.5 years prior to the first crew arrival. With the required machinery, the resources for establishment of Martian habitat, they include everything from the powerful Martian rovers, 3D printers for habitat, etc. The vehicle will be initially charged and the preliminary objective will be setting up the kilopower units to commence the power production. The power is stored in the batteries and is used by the vehicles. Within half year of continuous operation, two habitats will be completely built and the ECLS system nourishes the habitat with ideal atmosphere. As more ECLSS units are brought, more habitats will become functional for the crew. The crew begins with the initial task of setting up the hydroponic gardens, setting up the proper ventilation, fire and safety systems, etc. As more units get built, more crew will arrive on the Mars. Then the crew can divide the task among themselves, as well as hydroponic garden, resting units, healthcare units, and other facilities can be allocated between multiple habitats. In order to build the habitat, we will utilize the in situ resources, thus reducing the dependency on Earth. Our proposed solution is to use Marscrete, also known as Mars concrete, to build the habitat. The basic composition of the Marscrete are basanite, kaolinite, sodium, and silicon. Using the Marscrete, the habitat will be built. The process will be additive layer by layer 3D printing. The built habitat will have the following features: a completely sealed habitat with suitable environments, having enough strength to withstand pressure differences and variation in temperatures, Materials are added with cork to prevent ductile to brittle transition. All corners are rounded to prevent stress concentration. The windows are protruding out and the upper structure is kept at 30 degrees to prevent radiations coming in. The bottom layer of the habitat is constructed underground so that the habitat can be built up to 3 layers without compromising strength, while the ground layer is heavily protected from the radiation. Tunnels are constructed for each sea transmit between the habitats to minimize the air loss. It also serves as an emergency exit at the time of contingency. The adoption of the vertical cylinder design provides the best formal basis for the Martian habitat. The above ground layers are protected with high-density polyethylene shading. Now, for this project, we are trying to explain more about on the environment control and life support system module, which is used as a life supporting for the Mars habitat. The ECLSS is a central module with the multifunctionality. It contains subsystems to maintain suitable temperature, pressure, air quality, provide potable water, and many more. During the pre-crew arrival, it will prepare environment for the astronauts. It will continue its operation to maintain proper environment for them to sustain. The subsystems of the ECLSS are discussed below. First, we shall look into the atmosphere management system. It is built to face the challenges that the atmospheric composition of Mars primarily consists of carbon dioxide, nitrogen, argon, carbon monoxide, which are not suitable for the crew. So it has to be converted to suit the crew as well as maintain the atmosphere for a very long period of time. To do so, AMS has the following subsystem. Now we shall study the oxygen generation system. This system is supported by MOTSI and electrolyzers. MOTSI. The working of MOTSI is that the compressed carbon dioxide is given to the solid oxide electrolyzer. The input gas is preheated and has pressure maintained at 1 atmosphere. MOTSI operates at 800 degrees Celsius and the pressurized carbon dioxide flow over the catalyst cathode, which splits carbon dioxide into carbon monoxide and oxygen ion. The carbon monoxide is exhausted out and the oxygen ions is electrochemically driven into the solid oxide electrolyzer to the anode for oxidation. The oxygen ion combines and produces gaseous oxygen which is released through the anode cavity. Then we store this oxygen in the oxygen accumulators. Next, we move into the electrolyzers. Polymer electron membrane (PEM). Water electrolysis process is a simple and effective method to split the oxygen and hydrogen. It contains the following parts. First, cathode. Cathode is made with platinum or palladium, which creates a hydrogen evolution reaction. It is further coated with electrocatalysts such as platinum or carbon. Second, anode is made up of lithium oxide or ruthenium oxide, creates an oxygen evolution reaction. It is further coated with the electrocatalyst pyrochlore. Finally, the proton conducting membrane is made with solid polysulfonated. It works like this. At anode, the water gets split into proton, electron, and oxygen. The oxygen is stored in the oxygen accumulators. The proton passes through the proton conducting membrane. Electron from the external circuit comes to the cathode. In cathode, the proton and electron recombine to produce the hydrogen. Next, we are going to discuss the other units of the AMS. We will begin with the atmosphere monitoring system. It provides a measurement of each gases in the atmosphere. Atmosphere monitoring system is kept at all habitat. This habitat intakes air in required quantity. A single focusing mass spectrometer bombards the molecule of air with electrons to form the ions. These ion particles are accelerated into the magnetic analyzer and based on the mass to charge ratio, they are separated using the magnetic field. On the focal plane, multiple Faraday collectors are kept to collect the required ions. The separated ions are kept in individual chambers. Oxygen, nitrogen, argon, carbon dioxide, hydrogen, carbon monoxide, and water vapor are separated in this method. Collected ions have the capacity to generate electricity, which are amplified by the electrometers. This gives data to the master computer, which can measure the partial measure as well as give required changes in the atmosphere. Now we are moving into the trace contaminant control. Due to various reasons, there could be chemical contaminants in the atmosphere. It is removed using this control. This system contains canisters with bed of activated charcoal and 2% plutonium on charcoal. Therefore, 3 canisters are required for each habitat. With a single pass, about 30% of the carbon monoxide can be removed. Both organic and inorganic airborne contaminants can be removed through the system. The lifetime of each canister is about 1 hour. A table containing maximum allowable concentration of some chemicals for a prolonged time is given below. Now we are moving into the high efficient particulate air filter or HEPA. With long stay on Mars, the atmosphere inside the Mars habitat can accumulate with submicrons or nanoparticles of dust. It contains several hundreds of layers of fiber. Still, a typical HEPA is about half a millimeter thick. Particles of different sizes are captured in different mechanisms. They are the imperial impaction mechanism. It is for the large particles and it is directly hits and impacts the fiber surface and adheres to it. The interception mechanism. Some particles are sufficient with sufficient contact time can also get trapped into the HEPA. And finally, the diffusion process. Last and very small diameter particles, due to randomness of diffusion collision, the particles has a chance to approach the fiber surface and also can get trapped. HEPA possesses an advantage that is almost 100% efficiency and pressure difference across the system is also very less. We are moving into the fire and the safety system. To manage the fire on the board is a very crucial thing. Crew training is also a very important concern. Time response of the crew can suppress a fire from the early stage. The detection unit contains dual sensor smoke detector. The signal is channeled to the master computer. The master computer will immediately close the ventilation and power to suppress the fire from spreading. System will now spray fire suppressant chemicals. Chip embedded on the crew, portable carbon dioxide mixed spray will aid protection from fire. Now we are moving into the post-fire atmosphere recovery subsystem. It uses the available HEPA filter along with a cartridge storing precious metal granules with high catalyst activity. It can be used for approximately 90% in conversion of harmful gases from fire into less harmful substances. Now we are moving into the carbon dioxide removal system. A four-bed molecular sleeve is a prime method for the removal of carbon dioxide. Initially, the air is circulated inside the Decian bed arrangement, which aids the removal of moisture content. Then the air is passed to zeolite, where carbon dioxide is removed. The air is then circulated back into the Decian bed previously used. This will allow the dry air to regain its vapor. We are moving into the pressure management system. The pressure management, the total pressure of the system is measured using a dual active variable reluctant transducers. We will now move into the humidity control system. The humidity in the atmosphere of the Martian habitat has to be maintained at right level for the proper functioning of the crew systems. Relative humidity is the measure of humidity. It is the measure with a device called hydrometer, which hydrometer. A 60% relative humidity is required. If the humidity is high, temperature inside the TCS will condense the vapor and remove the water content. If the humidity is low, then a spray of mist will increase the humidity. Ventilation. It is used for the uniform distribution of the atmosphere. Ducts and vents are of standard dimension for versatile purpose. Ducts can carry duct fan, which helps in recirculation of air. Of 4 to 20 times of recirculation of air is proposed. Water management. It is devised to provide potable water to the crew. Potable water is an essential requirement for the crew. The water is temporarily stored in the wastewater tank. Then it is taken to the mostly liquid separator where gases are separated. Then it is passed to a separate filter to remove contaminant that causes odor. Then the water is passed to the particulate filter, which is continued to the multifiltration where the inorganic and non-volatile organic contaminants are removed. The gas separator removes excess oxygen. Finally, an ion bed removes the dissolved products of oxidation, and the iodine is added to remove the microbials. Potable water is then distributed by the master computer. After the water processing unit, we shall now look into the temperature control unit. TCS uses a mechanically prompted liquid in closed circuit to perform mainly three functions: heat collection, heat transportation, heat rejection. Wastewater is removed in two ways through cold plates and heat exchangers. Both of them are cooled by circulating ammonia loops. Thermocouples are used to measure the temperature. The refrigeration is for the food storage. It is maintained at 3 degree to 18 degrees Celsius. Once it requires 800 degrees Celsius, so nichronium strip reduces the temperature and the temperature is maintained thermally insulated using ceramics. In order to increase the efficiency, we have arranged such that the thermodynamic process acts such that the heat source is the electric resistance coil and the sink is the glacier melting unit. Now I call upon Vishal to discuss about the waste water processing unit.
Thank you, Sally. Good afternoon. So I will be discussing about the wet water processing unit. We employ a technology called CELS to do the same. CELS is an acronym for Controlled Ecological Direct Support System. The regenerated resources from the solid waste generated on board could be used as fertilizers for growing plants in specialized enclosures. The process utilizes a combination of photosynthetic and degradative phases, and the basic technology aiding the process is referred to as composting. The entire process is centered around the microbial self-heating of organic assemblages. There are two types of bacteria used, namely the mesophilic bacteria and the thermophilic bacteria. It involves the interaction between a moist solid phase and a gaseous phase involving the interstitial air. The operating temperature of the process is centered around 45 to 50 degrees Celsius, and the optimum concentration of oxygen is maintained at around 20%. The entire process is governed by three process control regimes activated at different stages. Namely, the first process control regime is activated when both the temperature is below the 56 degrees Celsius and the oxygen concentration being below 15%. It results in the process gas being recirculated through the internal standpipe as shown in the previous figure. The second process control regime is activated whenever there is a violation in the oxygen concentration, namely when the concentration of O2 falls below the 15%. Now, this stops the recirculation of the process gas and causes the ambient air to be forced through the system, which in turn prevents the recirculation of the process gas. Now, the primary objective of the secondary regime is for the removal of the excess temperature, maintaining it at the optimum level. The third regime is activated in case of a temperature violation, meaning the temperature goes above the optimum limit of 56 degrees Celsius. This in turn results in the shunting of the process gas, whereby it passes through the heat exchanger, whereby it is cooled before being recirculated through the plenum. It is regimen 1 that predominates, and the composting cycle will be terminated. After a quality check verifying the quality of the compost and it being deemed suitable for use as fertilizers, the chamber is evacuated and the compost may be delivered to the farming site of the Martian habitat. The size and number of composting chambers depend on both intrinsic factors like the rapid decomposition and the existing factors like the size of the cold storage facility, etc. As part of the in-situ resource utilization, we employ a system called MARS, or the Mars Atmosphere Resource Recovery System, for trapping the gases. The Martian atmosphere is constituted predominantly of CO2, accounting for nearly 95% in addition to nominal concentrations of nitrogen, oxygen, and argon in the following ratios as shown in the slide. It is nothing, MARRS is nothing but a physical process that opts for a direct extraction of oxygen, water, and other valuable constituents from the Martian atmosphere. The operating temperature of this process is limited within the range of 400 degrees Celsius. The process is initiated by the supply of filtered gas followed by a multi-stage compression involving a primary and a secondary unit. While the primary steps up the pressure from 6 to 20 bar, the secondary steps up the pressure within the range of 30 to 100. The high pressure complemented by the low temperature of the Martian environment causes a quick liquefaction of CO2, results in us obtaining what is known as LCO2 or the liquefied CO2. Now, this is followed by a stripping operation which recovers the low concentration gases, namely nitrogen, oxygen, and argon, from the liquefied CO2. The secondary compression of the LCO2 causes the water to condense as ice, which may be removed using hoppers. The cryogenic distillation is then further employed for the separation of the individual constituents. The air is compressed and cooled to negative 200 degrees Celsius, and then there is a high pressure column as liquid, following which the nitrogen boils off at negative 196 degrees Celsius, the oxygen at negative 183, and the argon gas is formed as a byproduct of oxygen and separates at negative 186 degrees Celsius in a side column. These separated gases are then stored in individual containers and are used for various applications. In addition to this, we also employ what is known as a glacier melting unit, which melts the glaciers, and the ice obtained and the melted ice and the consequent water obtained is stored in the containers. Now, an overview of the ECLSS will be shown in the slides now. Next, we are going to discuss about the transportation, that is the development of Martian rovers. The Crew Transportation Rover is designed to prepare crew for Mars exploration. The 4-meter tall, 8-meter long, and 4-meter wide rover will be a state-of-the-art intraplanetary transportation rover. The rover will be able to run completely autonomously and can be controlled from the local habitat and can also communicate via satellite. With the help of multiple rovers on site, the crew can explore distant locations far away from the habitat. This rover also carries what is known as a mobility chassis. This allows the transportation of goods and carry other bulky tools for the exploration. The primary elements of the rover are as discussed below: the rover control unit, the crew resting unit, the airlock unit, the mobile ECLSS, the experimentation unit, the external tool unit, and the energy source. The rover's wheels are made with a large radius of almost 1 meter and a width of 0.6 meter. It also has gaps on the surface that allow sand to pass through them, preventing it from clogging up. The large radius of the wheel gives good ground clearance. It also has a 6x6 configuration. The chassis of the rover is designed to obtain a minimum inner turn radius. Now, we come to the radiation protection unit. The radiation protection unit for the rover employs a passive and an active unit. While the passive protection unit uses lead shielding or using hydrogenated boron nitride nanotubes, popularly known as hydrogenated BNNT. These are nanotubes made from carbon, nitrogen, boron with empty spaces interspersed using hydrogen. The active protection unit employs what is known as the electromagnetic shielding, which essentially produces a geometrically solenoid magnetic field around the rover. It is basically a pumpkin configuration using a multiple toroid magnetic system is basically utilized for the system. Now, next we are going to discuss about the power generation system on the Martian habitat. The primary objective is for the development of an in situ energy generation system on Mars. It should be capable of powering the entire human habitat with sufficient potential for scalability in the future. Now, we have calculated the power requirement for the Martian habitat within the range of 250 kilowatts. To satisfy this, we have opted for a primary and a secondary source, taking into consideration the factors of scalability, but also the factors of contingency in case one fails to deliver the required load. The kilopower reactors, owing to its highly compact nature and the power to weight ratio, has been decided upon as a primary source. This novel technology was developed by NASA and uses nuclear fission for the generation of electricity. The reactor has 7 main components. The core constructed using the highly enriched uranium-235 molybdenum heat alloy segments. It is an immense heat generated from the radioactive decay of the U-35 that provides the required energy. The beryllium oxide neutron reflectors directs the escaping neutrons back into the reactor core, thus maintaining the power at the required level. The sodium heat pipes attached to the core carries the heated vapor to Stirling energy converters, which converts the mechanical energy into electricity. Adequate radiation shielding in the form of lead shielding is employed to protect the habitat and its inhabitants from radiation. The control rods made of boron carbide or the start-stop rod are used to control the reaction and are pulled out completely only once the reactor reaches the final destination. The Stirling energy converters basically act as energy conversion devices. The factors of reactor safety and the design configuration are employed here. The secondary source, it is decided upon to use solar panels or the energy generation using photovoltaic arrays. The challenges of employing solar panels on Mars are discussed in the slides below. It is proposed that the output of the solar panel would have about 10 kilowatts and the solar panels used on the planet will have a 30% efficiency with a specialized use of triple junction cells. Next, we come to the power storage apparatus, which involves the use of battery. The primary objective is the storage of large amounts of energy required to sustain the human habitat on Mars. The required battery capacity has been estimated at 250 kilowatts. Now, this is extremely critical in times of contingency and during specific periods of the day when solar power generation is not possible. Now, the proposed battery design is made of molten salts that separate naturally to form dual electrodes on either side of the molten salt electrolytes. The anode is made from a lead bismuth alloy, the electrolyte being a mixed hydroxide halide having medium density, and the cathode being made of sodium metal. Upon heating, owing to differences in density and immiscible nature, they naturally become 3 immiscible liquid layers, eliminating the requirement of membranes and separators. During charging, the ions deposited at the bottom layer returns back to the top layer, resulting in the purification of the electrolyte. While discharging, the ions flow back to the cathode, thus feeding the rod. Now, a power distribution table will be shown to you. Next, I invite Thomas C. Francis to speak about the communication apparatus to be installed on the habitat. Thank you.
Thank you. The communication between the isolated habitat structure is very important for the passage of various information. For this, we use a telecommunication system based on a constellation of lower Earth orbit satellite that orbits Mars, providing mobile communication and high-speed internet across access for our self-sustaining colony on Mars. This system requires very short trip time progression on Mars, which enables us to make us common communication standards and protocol. They offers large margin coverage and high-speed installation and cost effectiveness. This network of communication satellites are interconnected Martian habitat, rovers, landers, ground satellites, orbiters, and relay satellites. Now we will talk about the our food. Food is the key element in survival. Food with essential nutrients provides energy for activities to improve metabolism of human body, ensuring healthy immune system. In first step, food can be produced by cultivation. Even though the Martian surface is not favorable for the cultivation, we have to we use a vertical hydroponic farming technique. The principle is simple: providing plants what they need when they need. They this is a cultivation without using soil. The saplings are planted in an inert growing medium supplemented with nutrient-rich solution. It has a control over the environmental conditions, including temperature and pH balance. Here are some elements used in hydroponic technique. A full spectrum LED is used to provide heat and light to the plant and illuminate the farm. Air conditioning system to circulate and cool the air. Osmotic system to purify water. Air humidifier to humidify the air. Controllers and automation system helps to control the system inside without human interference. The computers and modem is used to log into the IT system and enabling a remote operation of the farm. The polyurethane sponge is used as the growing medium. This is all about cultivation. Now, our next step is the selection of the plant. For cultivation, we have a chart of calorie, yield, and time period of some crops. For a man of reference body size and age, the average allowance is 2,900 calorie per day, and women it is 2,200 calorie per day. So our crew is of two men and two women. In total, allowance is 10,200 calorie per day. The average time period of harvesting is 4 months. So for 4 months, we have to produce food for about 12 lakh calorie. From this chart, we have cultivated 34 meter square area of each crop in three layer on two sides. By calculation, the setup can produce food of about 48.3 lakh calorie. In this, 20% is the losses and 38.6 lakh is the food produced. In the second part is the production of meat. Now, not only the vegetables provide nutrients to our body, also non-vegetarian nuts also provide proteins and vitamins to our body. So the meat production can be done using a bioreactor to grow. The type of meat is called cultured meat. Here the stem cells are derived from muscle cells and the muscle cells will multiply into 1 trillion cells and cells will naturally merge to form a myotube. All myotubes will combine to form a muscle tissue and this will form a piece of a meat. And our third part is the algae cultivation. The algae is a protein-rich species and can be considered as an alternative source for protein. Certain type of algae such as blue, uh, uh, blue-green algae consists of 60% of protein. So for the algae cultivation, we use a photobioreactor, and the post production is our next step. Here, the wheat and grains that we have to converted into powder using a grinding unit, and the vegetables that we cultivated should be dehydrated and stored in a closed container. Thank you. I will call about Vishal to concluding the program.
Thank you, Thomas. We have finally reached the conclusion of our presentation. After considering the several extraterrestrial bodies for the establishment of a human habitat, we finally settled upon Mars owing to the reasons described in this presentation. The exploration of the red planet is only the first of many forays of the humankind into outer space. Through our presentation, we have tried our level best to address the challenges at hand and are pretty confident that the technologies in use today and those in development will be sufficiently able to successfully complete the mission of establishing an extraterrestrial human habitat on the red planet. Thank you. That will be the end of our presentation.